Hello, in this video we're going to be looking at our second classifier, which is going to be the naive Bayes classifier or naive Bayesian classifier. This classifier is based on Bayes' theorem, which is using probabilities, and it is based on the assumption that the predictors are independent from each other. So in simple terms, the classifier, naive Bayes classifier, assumes that the presence of a particular feature in a class is unrelated to the presence of any of the other features. It's a very easy model to build, and it's particularly useful when you have large or very large data sets. We can look at the formula for Bayes' theorem, where we're going to be calculating the posterior probability for a class C given the existence of the predictor x. And the formula to calculate that value is equal to the likelihood of predictor x in class C multiplied by the class prior probability for class C, and all of this divided by the predictor prior probability. So this is the Bayes theorem. How do we use it in the algorithm? So first of all, we're going to create a frequency table for the dataset. We're going to calculate the probabilities for each of the classes. And then we're going to use the naive Bayesian equation to calculate the posterior probability for each of the classes. And then for the class that will have the highest posterior probability will be the outcome of the prediction. We're going to have a look at an example with numbers. So in this example, we have training data for weather, and the target value, the class, is whether they played with that weather or not. So we have a soccer team that we have the value for the weather for the day, rainy, sunny, overcast, and then the output is a yes/no, depending on whether they actually went out and played soccer or not. Okay. So our problem could be the sentence, players will play if the weather is sunny, and we want to know if this is correct. So we have sunny is going to be our new input, and we want to know if the prediction is yes, they will play, and the same for the other features, overcast and rainy. Okay, so we're going to start step number 1, convert the data sets that we had into a frequency table. What we're doing here is put in all our features, our predictors, overcast, rainy and sunny, and then the outputs, so whether they played or not, no's and yes, and taking the values from the table. So we have sunny, no, sunny, yes, sunny, yes, sunny, yes, sunny, no, and those are the values that are going to go here. For sunny we have 2 no's and 3 yes, and the same for the other ones. Okay, then we have the total values 5 and 9, so we have 14 games that we have recorded the weather and whether they played or not. The next step is to create the likelihood table, finding the probabilities. So basically we're going to calculate the probabilities per row and per column. So for overcast we have 0 and 4. There's 4 times they didn't play out of the 14. For rainy there's 3 and 2, so there's 5 times that it was rainy over the 14. Then sunny, there's 5 times that it was sunny over the 14. Then there's going to be 5 times they didn't play over the 14 days, and there's 9 times they did play over the 14. That is giving us our probabilities here, 0.36, 0.64 for playing or not playing, and then 0.29, 0.36 and 0.36 for each of the 3 weather. Now we're going to use those values to calculate use the Bayesian theorem and calculate our posterior probabilities. So remember our problem, it was sunny. What's the probability that they will play? So we're going to calculate the value using the formula. We have the probability sunny. If it is a yes, we have our 3/9. And these values are coming from our table. Sunny and yes is this box here, 3/9. For sunny only we have 2 and 3, 5/14. That's a value over here. Then probability of yes playing is this value here, all the times they played over the 14 days they played. And then we put all that in the formula and calculate the probability of playing when it's sunny is 60%. If we do the same for probability of not playing when it's sunny, we get a 40%, and so obviously the yes class is the winning class for this particular when the predictor, the input is sunny. You can do the same for rainy and overcast. Okay, so this the test set would be sunny, and we got out of these values, we decided that the prediction is yes, the team will play. Okay, so what are, to sum up, the pros and cons of the naive Bayesian classifier? Well, it's an easy and fast algorithm to predict a class for a test dataset, and it performs well in multi-class prediction as well as binary prediction. When the predictors are independent, the naive Bayes classifier performs better compared to other models like logistic regression, and you also need a lot less training data for it. It does perform well when you're dealing with categorical input variables compared to numerical variables. And for numerical variables, it assumes normal distribution of your data. Okay, when we're dealing with categorical input variables instead of numerical variables, we can come across what is known as zero frequency. Basically, the problem will arise if we have a category in the test dataset that was not observed in the training dataset. In this case, the model will assign it a 0 and will never be able to make a prediction for that particular value. So this is a limitation of the naive Bayesian classifier. Another limitation is the assumption of independent predictors. In real life, it's nearly impossible to get a set of predictors that are completely independent. Okay, but in general, it performs well unless your predictors are highly correlated. It will give a good estimate that can be compared to more complex classifiers, and it will be a lot quicker and faster. Okay, if we look at the scikit-learn implementation of the naive Bayesian model or classifier, we can see that we can use 3 different types of classifiers. Gaussian, that will assume that normal distribution. You can use a multinomial classifier used for discrete counts, and you can use a Bernoulli classifier that is a binomial, so it's for binary when your feature vectors are binary. Okay, so this was a very quick overview of the naive Bayesian classifier. Now you have another video where I'm going to take you through a notebook, a Jupyter notebook, with an example of using the classifier, and you will have to complete an exercise and submit where we're looking at a wearable device and checking if the exercise the person is performing has been done correctly or not. Okay, bye.